Thank you for the opportunity to speak here. Wait, we need chalk. Good start. Right, okay. So I should maybe apologize because my abstract, I said I would focus on the proof, at least in the second half. But then I realized maybe not everybody knows everything about Motivic homotopy theory. So I decided to rather give more background and applications. But now I'm looking and basically everybody seems to be expert, so maybe. Okay, so bear with me. I do my best. So generalized slices of KO. Oh, also my handwriting's known to be terrible, so don't be afraid to let me know. We'll see what can be done. Okay, and also just for convention, throughout I'm going to fix a perfect field K. It's a perfect field, and it doesn't have characteristic 2. That's probably not strictly necessary, but yeah, it's going to make life easier, and also I don't know how to deal with it. So yeah, so then I should say that this entire idea, it's sort of based on a question of Markov-Schlichting, and yeah, so certainly there's a lot of that there. And okay, so let me start with the background. And first we have that, okay, this is KO, and it means Hermitian K-theory. So I think I should try to say like 2 words what Hermitian K-theory is. I'm definitely the wrong person for that. But okay, Hermitian K-theory. Also, I figured it's a trimester program on K-theory, so that's probably a good start. So what we do is we start with the scheme. And for me, this is going to be a smooth scheme over K. So this is a very safe situation. I understand that this can be generalized to, I mean, essentially the generality in which algebraic K-theory works, except maybe you need 2 to be invertible. But okay, so we're certainly 2 is invertible. Everything's finite type. It's as good as it can be, and so on. Okay, and then Hermitian K-theory gives you so-called Hermitian K-theory groups. They're going to look like this. Okay, these are abelian groups. And here M and N, they're integers. They can be positive, they can be negative, anything you want. Okay. And also, I mean, with K-theory, there's only 1 index. And also there, if you put a smooth scheme in, then it's already 0 if you put a negative number. But here that's definitely not the case. So basically you can take positive and negative integers for both, and it's not going to be 0. I mean, sometimes, but not in general. Okay, and also there are loads of notations. So first of all, there are 2 indices, and well, they're not quite on the same footing, and also you can somehow shuffle them around. That's what always happens when you have 2 coordinates. And then other people might write GW for Grothendieck-Witt groups. I think that's very reasonable. Some people write KQ, I think because of quadratic forms, because the characteristic is not 2. This also doesn't really make a difference. Right. For now, this is going to be it. And well, I won't try to give a definition of. Is there a clock? Yeah. Okay. I won't try to give a definition of what this is. I just give you some examples. So you can do K0, 0, spec A. Oh yes, of course, KO00. 0. Right. So A here is just some commutative ring. Well, of course, smooth. And so this is a scheme, okay, the spectrum. This is going to be some actual Grothendieck group of some category. So that's something I can pretend to understand. It's going to be K0 of a certain category, and the category is finitely generated projective A modules. And of course, with some extra data, and this extra data is a choice of non-degenerate symmetric bilinear form on A, with symmetric bilinear non-degenerate form. And so, for example, if you would take 2 here, then you replace symmetric by antisymmetric. And well, if you take 1 or 3, then you take something a little bit more strange, but also very concrete. And then, okay, I haven't told you what to do about the other possible values of M, but there's also this sort of standard trickery, which is that KOI n plus 4 x is just there's an isomorphism like this, so there's a periodicity in this n variable. In particular, this explains why it cannot possibly be connective in this n variable. Okay. Right, and so also in K-theory, you have in principle the same thing, except that the period is somehow 1, and then it would be a bit silly to carry it around. So we don't. Okay, that's the end of the super rapid introduction to Hermitian K-theory. Now we do Motivic homotopy theory, just as quickly. And also just as deeply. Okay, so stable motivic homotopy theory is essentially just the natural stable homotopy theory of smooth varieties. Right, so what I mean by this, that there's a functor, sigma infinity, and it goes from pointed smooth varieties to some other category, namely SH of K. Okay, this is some category, and I write like this, so it's the homotopy category of some stable infinity category. In particular, it's triangulated, it's symmetric monoidal, it's compactly generated, lots of good things. And so it's built essentially by, well, you take the pointed schemes and you first make it in some sort of homotopy theory in a canonical way. Okay, so pointed simplicial presheaves, sure. And then you have to do some localization. Well, surely you want to make the affine line contractible, because, I mean, that's how you sort of got from an abstract homotopy theory to something related with geometry. Then there's something technical called Nznevich localization. Let's just put it in. And then, okay, we said stable homotopy theory, right? So you have to stabilize something. And in classical homotopy theory, you stabilize with respect to the circle. But of course, if you invert some element, let's say A is same as just inverting A squared. So you could also just invert the sphere. And of course, geometrically, the sphere is P1. So P1 is our Riemann sphere. That's going to be invertible. By which I suppose if you take P1 pointed at any one of your favorite rational points, gives you an object here, then you apply sigma infinity, you get to here, that is going to be an invertible object. Okay. Now, there are a few more words to be said about P1. One is that I will often call it T. I mean, technically speaking, T is some, well, other motivic space which happens to be canonically A1 equivalent to this, but I'm only going to be working essentially here, so this is basically an isomorphism. And also, there's this funny thing that this is equivalent to S1 smash GM. So you see, if you invert P1, you invert also automatically S1 and GM. So somehow inverting S1 is a sort of well understood process of, well, stabilization, and then you invert GM, which, I don't know, somehow it's a reasonable thing to do from a geometric perspective and weight theory and stuff like that, but it's very hard to understand. Anyhow, we do all of this, and that's called motivic stable homotopy theory. Now, here are some example objects, which are nice. So this category is good, I mean, essentially for similar reasons why the classical stable homotopy category is good. So for example, you take a reasonable cohomology theory, should be representable in this category. And we can. So for example, there's the object called, well, I'm going to write it like this, HZ, and it's called the motivic cohomology spectrum. And it has the following property. If you do maps like this, okay, so you take yourself, what have I done here? This looks interesting. So you take yourself some smooth scheme X, you add a disjoint base point, this is what the plus means. Now you have a pointed smooth schemes. Then you can do the infinite suspension spectrum, you get an object in here, and then you map it into this twist, shift, whatever you want to call it, of HC. And out you get some abelian group, which is Hn plus. Out you get this group, which is known as motivic cohomology. And I mean, there are other definitions of motivic cohomology, which should, well, I mean, they could be defining this or the other. So, yeah. In our situations, if you write down a version of motivic cohomology, this is going to be it. And similarly, there's a spectrum called KO, and you can probably guess which cohomology theory it's related to. like this, sigma infinity x plus smash s. So here we do it like this. Somehow I've moved the s to this side, and instead of doing gm, I've put t. And well, so there are always choices, and change these coordinates around. And if I do it like this, then I get what I wrote before. So we get this. So Ka was also representable. And then there are some other examples. For example, there's KGL, which represents algebraic K-theory. And that would be something like the sphere spectrum, which, well, represents who knows what. There's MGL, which represents algebraic cobordism, and all of these things. And the cool thing about the Motivic stable homotopy category is if you try to say something, I don't know, about, if you come up with some way of describing one of these spectra, then it's automatically going to tell you something interesting about cohomology theories. Yeah. And so sometimes that is easier than sort of taking the definition of this and then trying to cook up something. I mean, yeah. So more approaches are usually good, I think. Right. So then I want to say something about filtrations. And I'm even going to have a definition. It's totally just for this talk, but there are going to be 3 examples, and so I just, well, have a definition which encompasses all of them. Filtration, well, with an F, of SH of K, is an increasing sequence of full subcategories Okay, and I'm going to generically denote them as follows. And it's infinite in both directions, in principle. And that there's going to be one condition, which is that these inclusions are supposed to all have right adjoints, such that this is supposed to have a right adjoint. And then you can see easily that any sort of reasonable thing, so this into this has a right adjoint, and so on and so forth. Yeah. Okay. Now, if you have such a filtration, and well, you have these right adjoints, and then given any spectrum, you will get a tower. And it's going to look like, it has a right adjoint, and I'm going to denote this right adjoint by FNF. So somehow like nth connective cover with respect to this filtration. Okay, and now if you have any spectrum, you will see that there's going to be a tower like this. So, like this probably. It's going to look like this, right? So in principle, you want to think that if you make this index here smaller, somehow this filtered category gets bigger, and so you get better and better approximation. That's a bad idea, yeah. So I think like this. Okay, so if you make this index smaller, you can go in this direction, and then the approximation should get better. And ideally, you should set things up in such a way that if you take the homotopy co-limit, you get back E. On the other hand, somehow the terms over here, there's somehow some sort of error term, and ideally you want to set it up in such a way that the homotopy inverse limit of these things vanishes. Okay, and if you have this sort of tower, you can try to understand this spectrum by sort of arguing layer by layer. And I'm going to give these co-fibers. I'm running out of space here, but that's the co-fiber, and it's going to be denoted in this case as 0F. E, and then you have another one here, S minus 1, no, minus 1, F. E, and so on and so forth at every layer. And ideally, if you understand all of the layers, and if your filtration is somehow good enough, then you can understand E. At least you can hope to understand it better than before. Well, I mean, if it was decreasing, you can just... yes. I think this is how it goes. I mean... yeah, so I think the spectra somehow get bigger, and you make from the small to the big things. I think that's how it should go. Well, it should, in this direction, it should get better and better. Exactly. So if you project into all of SHK, you're back to E, because, I mean, you're not doing anything.
The issue with line 3, your indices, your indices have been reversed from what you did at the bottom. It's not good.
I see what you're saying. That's correct. That's not a very good idea. It's also not what I have in my notes. Or is it? No, I think. No, but I think you're right. It should be like this. Okay. That's not so good. But we'll do 3 examples, so get 3 chances to check if my indices are right. Okay. And so I was going to say, okay, there's this business of trying to understand the layers and then trying to understand something about E. But of course, if you want to do computations, that's a code for doing spectral sequences. I would rather not do those. So I would just think about the tower. But in principle, to do a hard problem, that's probably what you need to do. And I mean, obviously, if you have a spectral sequence and you like spectral sequences, then you're happy. So I hope some of you are. Okay. So the first filtration. It's going to work like this. So it already has a name. It's called the sort of greater than or equal to n part in the in the homotopy T structure, and you can write it explicitly as the subcategory generated under homotopy colimits. And I'm going to say end extensions by sigma infinity x plus mesh s. By objects like this. So in particular, if I make n bigger, then this gets smaller, so I think Chuck had it, right? Okay, and then but also I'm allowed to take m in z, so I can desuspend by gm, but somehow in the Sn direction, I'm fixed. I mean, I could make n bigger. This is included in saying that it's close to the homotopy colimits, but I cannot make n smaller. Yeah, and also somehow this closure under homotopy colimits is already forced to you by the existence of this right adjoint, so that's not super surprising. The closure under extensions is not super obvious. Actually, I think in this case it's not necessary. The categories which you get is the same, but this is somehow the standard terminology if you want something inducing a T structure. It's just in this case, it's not actually necessary. And you should also see that this subcategory, it's definitely not a triangulated subcategory. And as I said, it leads to something called the homotopy T structure. And this is one way of filtering the category. And I guess the homotopy T structure in this context was first sort of written up by Morel, but it's also it's very similar to the case of, let's say, DM. And yeah, so Wolwodsky knew about these things, of course. Right. What do I know? Who wrote things first? But I believe I said what is correct. Okay, and then we're going to have some, okay, because this is a T structure, I'm going to use some special notation for this Fn and Sn. And in particular, I'm going to write, instead of Fn Fe, I'm going to write E greater than or equal to n. And instead of Sn Fe, I'm going to write pi n E star, and I suppose something like this. So it's customary to shift these homotopy objects so that they live somehow in the zeros layer. And then there's a star here, which I'm going to explain later. For now, it's just some notation which somehow is used for the layers. Who cares why? Here's an example. So I said there's the sphere spectrum, right? So this should have a pi 0. Classically, pi 0 is z. Here, not quite. It's something called unramified Milnor-Witt K-theory. Great. So now I've told you what it is, but right. I mean, again, it's K-theory, so that's good for the workshop. Apart from that, I would say I find it a bit arcane. So you can define it in terms of sections of a field, say, in terms of generators and relations. So in particular, if star is 0, you get something called the Grothendieck-Witt ring. It's also related to this. It's another great start. But yeah, I don't feel like I have very good intuition what this is supposed to be. But somehow, yeah, it's related to quadratic forms. It's related to integers. Yeah, it exists. We'll have more to say about it. Slow. And there's another example, which is pi 0 of HC, which is Milnor K-theory. So HC is Motivic homology, and here pi 0 is somehow not Milnor-Witt, but Milnor K-theory. And I think this is a much more classical object. I mean, it has an easier presentation in terms of generators and relations. I'm not sure if that makes it so much better, but yeah, okay. People have computed this. There's something explicit you can know about it. I think that's a good start. Okay, now up to filtration number 2. In this case, FNSH. Okay, also already has a name. It's SH. So it's the so-called N-effective spectra. And in fact, this can be written as localizing subcategory generated by these objects. Now, yeah, so all X, and you cannot desuspend by a GM. I didn't put any sort of S1 suspension here, but the point is that localizing subcategory already implies that you're allowed to suspend and desuspend by S1. So actually, I could have just taken the definition, this definition, and interchanged the role of Sn and Gm, and you would exactly get the other one. But of course, this one is now triangulated, so in some sense, it's a lot nicer. Okay, so let's try this whole dry erasing business. Sure. How do you feel about that? I don't know. Okay. So, as I said, this filtration leads to something called the slice filtration, which was definitely invented by Wojewodsky. Maybe I shouldn't say definitely, but I'm pretty sure. Excuse me. Oh, that's a very good idea. Yeah, how do I do this? Right, okay, so the slice filtration, invented by Wojewodsky, also has special notation. This is actually where I stole it from. So instead of F and Fe, I'm just going to write Fne. Oh, here's an E. Here's an E, like this. And SNFE, I'm going to write SNE. And again, can't really get into how you compute these things, but here are a few examples. So S0 of the sphere spectrum, again, should be something maybe related to the integers, and Olé, this time, it's actually HZ, exactly the same as classically. And also you can, for example, compute the slices of KGL. Remember, classically, it should just have homotopy group Z in somehow all even degrees, and in some sense the same happens here. You get this. And also, I mean, so far I've only told you about slices. Funny thing is here you can also say, I mean, give some examples where you can compute covers. Normally you just take a cover of something, give it a new name, typically by taking the same name and writing it in lowercase letters for some reason. But here we can do, for example, this. Effective cover of Milnor K-theory is actually HZ again. Sometimes people find this funny, but it's not difficult. If I have time, I will maybe give a proof, because there's supposed to be a proof in every talk, and this one would be easy. Right. Now, on to example number 3. This is the new one. Well, it's not that new, but so the very effective slice filtration, or generalized slice filtration. Okay, as I said, it already has a name, very effective slices. I think the definition was first written down by Spitzweg and Hausdorff. And actually we could define it as just the intersection of the other two. You can do it like this. Oops. It's not a very good N. But also we can give a bit more direct definition in terms of generators. It's the subcategory generated by objects of this form. And subcategory genet, I mean under homotopy colimits. And again, you could throw in extensions if you want, but they're somehow already in there. And you see here, now we've somehow suspended by both T and GM, by both S1 and GM the same number of times, and you're not allowed to desuspend by either. But of course, you can take more suspensions in either direction. That's always okay. Again, this is not a triangulated subcategory, so the slices are going to be not so easily approachable maybe. And also, this does not define a T structure, at least not on all of SH of K. So again, this no obvious long exact sequences and so on and so forth. It's a bit finicky to work with. Okay, so this leads to the generalized slice filtration. And I should maybe say this is also fairly closely related to the slice filtration in equivariant homotopy theory. At least there's a sort of real realization to C2 equivariant, and then they're really very close. Oh yeah, special notation for these slices. Okay, instead of F and E, I'm going to just put a tilde on this. And for the slices the same. And this is a long-standing tradition in the field. If you make a generalized version of something, you put a tilde on it. I didn't come up with this. And I can give you some examples. Well, obviously, the main theorem is going to be an example, but here's something we can start with. And this is kind of funny. Like this. So if you take the nth connective, sort of effective cover of the KGL spectrum, by some miracle, it's already very effective. So this allows you to compute the very effective cover. And in particular, I mean, it allows you to compute the very effective slices. Like this. And this is a sort of miracle which happens quite a bit. For example, the same is true for MGL, I think. Yeah, it's just somehow that homotopy groups tend to be concentrated in even degrees, and I think this is an expression of that sometimes. Right, so now that we have all the filtrations in place, just a bit more notation. That's exactly what every talk needs. Okay, we had HZ, and now we're going to make an HZ tilde. And maybe it's still here. I told you that HZ is actually equal, or I mean, canonically isomorphic to this. And in order to make a tilde, I'm just going to replace Milnor by Milnor Witt here. Where's? Oh no, well, it doesn't make a difference in that case. Yeah, so this is already very effective. good point. And also I want another version, which is somehow going to be with Motivic homology. And then here I dropped the M. It's an interesting trick. I mean, if you know about something called unramified with K-theory, then that's going to make you happy. Or, I mean, I can tell you that it can be described as Milnor-Witt modulo a certain element in weight 0, or degree 0, weight 0, I suppose, which is called H, which people are particularly fond of, and then they want to kill it. No, maybe they hate it, I'm not sure. And also, I mean, it's related. You see in weight 0, this is going to be the Witt ring, of course, right? Because, I mean, Grothendieck Witt ring modulo H. And then it turns out that in higher weights, this is just the powers of the fundamental ideal. So I feel like this is a bit more friendly than Milnor-Witt K-theory. And negative degrees, it's always the Witt ring, but that's also true for Milnor-Witt K-theory. So, yeah, I feel like this one I can relate to better. Now, finally, we can state the theorem. And of course, what we're going to do is we're going to compute the generalized slices of KO. There exist canonical isos so we want Sn tilde KO, of course. And so the first thing to note is that, as I said, KO again, it's supposed to be 4 periodic in this upper index, and also this upper index corresponds to smashing by T. And also smashing by T somehow corresponds to just going up sort of one layer in the very effective connectivity. So what you expect is that up to smashing by T, this is going to be periodic with period 4. So it must be something like T to the N, smash something, and this something is going to depend on N modulo 4. And unfortunately, we start out with a bit of a disappointment. If N is congruent to 0, then so far I'm not saying anything. Then, but now it's going to be more interesting. N congruent to 1, 2, and 3. So if it's 1, you happen to get H Z mod 2. If it's 2, you get H Z. And if it's 3, you get 0. Okay, now we say, but S0 tilde KO, I mean, that's not something I know anything about. And then I will say, okay, but there are 2 distinguished triangles which you can use to decompose this. So somehow the philosophy here is that T, which we are in some sense slicing with respect to, is a 2-sphere. And so somehow the layers should really be composed of 2 things. And here it's only 1, but this is somehow an accident. Whereas here this accident doesn't happen, so you have to do the honest thing. Also, there are, I don't know, canonical distinguished triangles. And there are going to be 2, because they're sort of 2 different 1-spheres, and corresponding to these 2, you get 2 different triangles. So one is HW smash GM, goes to S0 tilde KO, goes to HZ. Or you can do this. So in either case, on one of the sides, you get one of these sort of generalized or scary Motivic homology theories, and then on the other term is somehow going to be more familiar. And also, I would draw your attention to the fact that somehow, if you think of Witt theory as being a bit like modulo 2, because this H in some sense is 2, at least over C, for example. Somehow it's a 2-dimensional thing. So somehow on the left you get Z mod 2, and on the right you somehow get Z. And this is not really an accident if you think about the fact that we know the stable homotopy groups of KO just in topology, right? There's the spectrum of, I suppose, orthogonal K-theory, and its homotopy groups are known. They're 8 periodic, and well, they're exactly this, which I'm going to write down. Right, so my remark is this. If we look at pi star of KO, this is just topologically. Well, what you get is, okay, there's some negative terms, but I mean, it's infinite in both directions, so I have to start somewhere. Z mod 2, Z mod 2, 0, Z, 0, 0, 0, and then it repeats. And look, I said you have to somehow slice with respect to S2, so always two of them correspond together. So we should have this, 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 this. And well, it's exactly what you see, right? S0 tilde is somehow made up out of Z and Z mod 2. Okay. And then S1 somehow made up out of Z mod 2 and 0. And well, okay, here's the Z mod 2 and yeah, the 0 is not there. Then Z0 works, 0, 0 actually gets 0. I think that's very satisfying. Right, okay, so I think this is the statement of the main theorem, and it's the most important thing I wanted to get to, so that's great. I have much more I can tell you. Are there any questions so far? Apparently not, so I mean, of course. Well, I mean, what I mean is an object, this is going to live in SH of K hard under the homotopy T structure. But okay, so this is some code for objects in here, and how it works is that this hard can be identified with the category of homotopy modules, and the homotopy module is a sequence of sheaves on the category of smooth schemes, which are strictly homotopy invariant and have some delooping data. So yes, this is for every star, every integer star, you get a sheaf. And yeah, so the zeros one is width. So you take the sheaf of width, you take the pre-sheaf of width groups and sheafify it. And the next one, you take the pre-sheaf of fundamental ideas and sheafify it, and so on and so forth. Does that make sense?
Yeah, it makes sense. It's just, what is K and W scheme?
Well, it's an unramified, I mean, in principle, you can, well, MW is a bit hard, but I mean, in principle, it's unramified, so it's going to inject into the function field, and then it has.
You're basically defining on the function fields and then using, it's the homotopy modules of degrees.
Yes, but I mean, also I can define K star Milnor width just to be pi 0 of the sphere spectrum. I mean, that certainly defines me an object, but then you have to compute it, and you can check that it is what you say it is. Yes. Yeah. So so it's defined on fields and on discrete valuation rings, and there's some sort of boundary map, and yeah, it's in principle it's computable, but it can be a bit. Yeah, it is what it is.
What about these two? So APC tilde and HW are still sort of defined via the slices themselves.
I agree. So first of all, there's something called HC tilde in the literature, generalized motivic homology of Baptiste Calmès and Jean Fasel. And so far, it's not shown that these are the same. But I very strongly, I at this point, I think I would conjecture that they're the same. Yes, and also, so if I get to it later, then you can say more about this abstractly. But yes, I think they should be this concrete thing, which is something explicit in terms of cycles and orientations, and yeah. Okay. So I'm going to spend a few minutes to give you some idea of the ingredients of the proof, mainly because I need some of the ideas for the application if I get to it. Okay. So the first thing is that we need to understand a little bit better this homotopy T structure. And so I'm going to define. I wanted to, okay, so E is in SH of K. And I want to define a sheaf pi n of EM with two indices, and it's going to be a sheaf on the category of smooth schemes. And in fact, it's the Nisnevich sheaf associated to or with, I can never remember, probably associated with. And with a particular pre-sheaf, and this pre-sheaf is X maps to Right, so here's yet another way of shuffling the indices around, and for some reason this is very convenient. And the point is that, of course, now I have somehow two notations pi n of E star, and well, of course, the secret is that they're the same. And this is, so in some sense, this is the main observation of this homotopy structure of Morel business. And then we can explicitly describe this sort of this homotopy. Yeah, so the connective covers or the categories of connective objects in the homotopy T structure. So you get this, then right. So I can give you an explicit criterion in terms of these homotopy sheaves for something to be in here or in here. It's going to be as follows. Well, it's exactly as in topology. It's those E and SH. Right, so the criterion is, if you want to be non-negative, then all of these pi n of em, where n is less than 0 and m is anything at all, they all have to be 0. Okay, so it turns out that this is the correct definition. And the main point which I want to make is that you can define in a very similar way a T structure on the effective spectra. And I think this was also known certainly to Spitzweg and Hausdorff when they wrote down their definition of very effective objects. Similarly, SH of K, effective, greater than or equal to 0 or less than or equal to 0. It's like this. So in this case, you don't ask that it be 0 for all values of star, but just star equals 0. Of course, you see sort of the negative stars are determined by 0. So really what it says is that's true for all negative values of star, but not the positive ones, because somehow the positive ones correspond to desuspending by GM. And in effective spectra, you're not allowed to do that. Okay. And then so an example would be that HC is an SHK effective. This defines an object in the heart of the effective homotopy T structure. And I mean, in principle, it's easy to see. Oh, depending on what your definition of HC is, it's not at all easy to see. But someone will have showed that this is an effective object. And I think Wojcicki was maybe the first, and then positive characteristic Levine had some things to say about this. Okay, so it defines an object here, but now how do we check it's in the heart? Well, it says we have to compute the homotopy sheaf, so we need to know what is pi n of HC 0. But you see, this is weight 0 Motivic homology. That's something I'm very sure I can do. This is Hn, 0 of, well, something with coefficient z. So this is basically z if you have n, yeah, n equals 0 and 0 s. Aha, so it must be an object of the heart. And then I can prove that this outrageous claim which I made earlier. And well, I mean, by now it's sort of easy, right? So we consider HC. It's actually very effective. I mean, that is certainly correct. Yeah. So we take HZ. We know that it is it's non-negative in the homotopy T structure, so we can map it to its pi 0. And we know that this is Hermitian K-theory. And then, of course, F0 is a functor, so I apply this functor. And then we already said that HC is effective, so F0 doesn't do anything. So it's equivalent now to HC. So we have now exhibited this thing as a map between effective spectra. And in order to prove that it's an isomorphism, I just have to check it on homotopy sheaves. Check iso on right? And the whole point is that because it's effective, I only have to check it on a 0th degree homotopy sheaf. And I already told you, this one is Z in degree 0 and nothing else. And what is this? Well, Milner 0 I can also do, that's Z, and Milner 1 is GM, I can also do that, but then it gets hard. But so certainly this is Z in degree 0, and then somehow because it's already in the Hartmann building, this doesn't change. So yeah, so the homotopy sheaves are the same, and it's easy to see this is an isomorphism. Okay. So at least here we have a proof. And then maybe, okay, so two more ideas for the proof of the main theorem is one is the so-called algebraic Bott sequence, I think. And it says that there's a distinguished triangle. It goes like this. And the idea for using this in the proof is that, well, you know somehow things about the very effective slices of this. And somehow let's say the very effective 0 slice of this seems to be related to the very effective 1 slice of this. So if you, and also you know that these slices are periodic. So the idea is that somehow, since you know everything about this, as soon as you know, let's say, one thing about this, you will know one thing about this. But then this is going to be the next for this. And so somehow if you know one, you can work your way through. And then after 4 steps, you're already going to be done. So this means you only have to compute one slice. Reduced to 1 slice. In fact, to any one very effective slice. And it turns out the easiest one is KO smash T squared. And here what you do is you use that this is related to symplectic K-theory, and it's representable by somehow quaternionic Riemannians, and then the geometry of quaternionic Riemannians has been studied carefully. And then you use a certain trick of Wolwatsky, which, I found it in a paper of his where he talks about the slices of KGL, I think, for the first time. And so basically, what this means is you can reduce to a certain statement about quaternionic Riemannians. And then you read basically the introduction to the Panin-Volta paper about quaternionic Riemannians, and it turns out you can do it. So it's a reasonably straightforward adaptation of Wolwatsky's strategy with the extra work of Panin-Volta, and then, well, you can fight your way through. It's all I want to say for now, because I have like 10 minutes and I want to say some fun things. Of course, maybe there's a sort of zeros level application, which is that you get a spectral sequence computing Hermitian K-theory. And by design, it's going to be strongly convergent. And the E1 or E2 or whatever way you index your page is going to consist of various versions of Motivic homology. Yeah, so I think if you want to know something about Hermitian K-theory, that's not a bad place to start, because ideally Motivic homology should be more computable than Hermitian K-theory. It's a bit debatable right now because the definition of, well, HC tilde is F0 of something. I have no idea how to compute that, but, well, time will tell. As I said, I think it should be the same as what Calmes-Fazel write down, and then that is, at least in principle, computable, although it's still super hard. Okay, so the first fun application is a sort of Motivic connective KO theory. Right, so this is my proposed definition of Motivic connective KO. Actually, I'm sure Spitzek Oistwa wrote down the same thing, but maybe they did KGL. So I'm not. This is going to be it for the talk today. And then there's also KGL, which of course I should write to be consistent at all, but as I said before, it's actually the same as F0 of KGL. So here it doesn't make a lot of a difference. And actually, maybe I should say that the reason why this is true is essentially because algebraic K-theory of regular schemes is connective. Okay, what are we doing? Ah, right. So I claim that this algebraic Bott sequence here also holds if I make everything into lowercase letters. Okay, and so, well, maybe we do a second proof. It's probably my best talk ever. So the co-fiber of this map, this is what I want to analyze, right? And in the end, I want to show that that it's this lowercase KGL. Let me call it X. Then X is very effective. And the reason is just, well, KO is, I don't know, connective KO is very effective by definition. Right? Then smashing with GM doesn't destroy very effectiveness because GM is also very effective. That's okay. And then a co-fiber is some type of co-limit, which are also allowed to do. So this is very effective. Great. So it means in order to prove that X is the same as KGL, we can just check it on the homotopy sheaves in degree greater than or equal to 0 and in weight 0. So hopefully that should be easier. So it suffices to prove the following. And also, of course, you see, I could put KO here, but if I now do degree 0, and if I do something here greater than or equal to n, it's going to be the same thing as if I put the ordinary KO here, just because of the way in which the homotopy sheaves are set up and the way that this functor is a right adjoint. So this is not a problem. And then, if you think about it, it turns out you need to prove that there's a surjection like this. This is not the only thing you need to prove, but this is one of the things which you need to prove. And well, okay, this we can do. Pi 0 of KGL 0. This is somehow Z. Well, I suppose it says that the finite dimensional vector spaces of a field are indexed by the integers. And this turns out to be GW, our good friend again. And this is the rank map, and it's a surjection, because, well, every finite dimensional vector space supports some choice of symmetric bilinear non-degenerate form. Okay, and you need to prove a second thing. You need to prove that pi n of you need to prove this because, well, I mean, you see, the pi zeros of KGL are supposed to be the same of connective KGL are supposed to be the same as the pi zeros of the non-connective KGL, and it sits in this sort of triangle. And somehow we have replaced the middle one by the lowercase ko, but besides it has the same homotopy group. So if this is supposed to be true, then on the left, this must also be true. I realize this is not a super good explanation, but if you think about it sort of by yourself without pressure for 10 seconds, it's obvious. Okay, how do we do this? Well, I mean, okay, let me just deal with sections over K, but this immediately generalizes, then this is going to be right? Essentially, by definition, it's this. And then, well, you see, GM inverse is not effective. It's also not very effective, of course, but it's very -1 effective if you want, because sort of T inverse smash S1, and you're allowed to smash with F1. So this is going to be the same thing. Same thing as this. No. Of course, I just explained, you need to put a -1 here. But now you see, well, you don't because I erased it, but the difference between F0 and F-1 is measured by S-1. And S-1 is congruent to 3 mod 4, and we had a 0 with a 3. So actually, right, so this is going to be the same as simply because S-1 tilde KO equals 0. So this is a corollary of this computation. But now this is the same by definition. So we're done. And maybe to make it clear that this sort of connective Bott sequence is not entirely idle-musing, I should say that it has the following interesting consequence. So there are somehow, I don't know, I don't want to say the word chromatic because I don't actually mean, but something lower chromatic something, analogs of this, and it goes there's a distinguished triangle like this, and the reason is essentially that this is just f1 of KGL, and then, yeah, so this is f0 of KGL, we already said that that's true. And then there's another one, it gets more and more trivial. So you have these sort of three distinguished triangles, and somehow you can believe that you understand this very well, but this not so much, and then you understand this very well, and this not so much, and somehow you can fight your way up. And the plan, the aim of the game is then to compute the motivic homology of these things. And then, well, the point is you can do this exactly as in topology. So using H star star right, so you take this spectrum representing motivic homology, and you take mod 2, and you take its mod 2 motivic homology. So it's like the strangest thing ever, but it turns out this is called the motivic Steenrod algebra, and this was computed by Wojewodsky in some sort of explicit form. And then you do the same thing with HC. And as I said, right, just from this sequence, it's not super obvious what it is, because you have HC twice, and this what so you don't know this, and you know only one term. But somehow the point is that this map is 0 in cohomology, and then you can fight your way through, and then one gets the familiar answer. Right, and so I don't want to say what this means. So either you know some topology and then you recognize this, and again it makes you happy, or you don't, and then you just zone out for 30 seconds. And you keep going. You do KGL, and you get A star star mod mod A star. Oh no, E star star 1, I think. Right, so this is just a 5-second reminder. This is generated by Q1, and this is generated by the first Milnor operation. So it's sum. And now we're going to get to the new one. So I think, I mean, as I said, this is Wojewodsky, and I think this is more or less known. It's, for example, in the paper of Dagger. And then you can do KO with C mod 2, and you get A star star mod mod A star star 2. And so somehow for topologists this is very important, because I don't know, for them this is essentially the definition of KO. So I think in this paper which I just mentioned, Dan Dagger said, so what they do is they construct some cellular spectrum over C, which they call KO, and they prove that it has this cohomology, and say like, yes, we found the right one. But also they tried to, of course, relate it to geometric things, and they said you could do, well, I don't think they wrote this, but he said to me, you can do this truncation, and it doesn't seem to work, and you can do this truncation, and it doesn't seem to work, and well, it doesn't work because you have to do both at once, so I thought that was a fun way to end it. Okay, so now I think I'm running out of time, so that's enough.